Hello, welcome to this talk on the Fibonacci sequence. I love this sequence. It's so much fun to play with. It's got so many cool little secrets, and you can walk around virtually anywhere in this world and see evidence of it. So, really exciting stuff. Before, though, we talk about the Fibonacci sequence, let me just kind of generally review what a sequence is so that you have in your head, you know, what's going on here. A sequence is a list of numbers, and there's some kind of a mathematical pattern to them. For example, an arithmetic sequence, you might say, okay, let's have this sequence start with the number 1, and let's have the pattern or the rule be that we add 3 to get the next element in the sequence. So if you know you're starting with 1, it's kind of your rule, one of your starting rules, and then you say, oh, okay, so I have to add 3 to get the next element there, so I get 4. Then I have to add 3 more, so I get 7. Add 3 to that, and I get 10. Add 3 to that, and I get 13, and so forth. Your sequence can be finite, so you can have an end, or it can be infinite, which is what I did here. I put those 3 dots, also called an ellipsis, to say it keeps going in that pattern, in that direction forever. So you don't have to do that, though. You can always end it somewhere. Geometric sequence, another example, maybe, where you might also start with 1, but with arithmetic sequence, we add a number. Geometric sequence, we multiply by a particular number. So if we did 3 again, this time instead of doing 1 plus 3 to get 4, like we did in the arithmetic sequence, we would do 1 times 3 to get 3. Then we would do 3 times 3 to get 9. 9 times 3 we get 27. 27 times 3 we get 81, and so forth. So, you know, we added 3 to the arithmetic sequence and we multiplied by 3. That's addition, that was multiplication, to get the geometric sequence. So that's kind of examples of sequences. There's all kinds of different ones, but those are just 2 examples. All right, so let's go to Fibonacci. Before we talk about Fibonacci sequence, let's just briefly mention Fibonacci. He was also known as Leonardo of Pisa. He was from Pisa. And we talked about the Hindu-Arabic number system in our first big unit in this course. That is, after all, the number system we've grown up with. He introduced it into Europe. It wasn't well known in Europe until he came around and said, hey guys, look. He also wrote a book called Liber Abaci, Book of the Abacus, way back in 1202, so it's been a while since he was around. And that emphasized the importance of the number 0. Because remember, a lot of number systems didn't use 0, didn't have a 0. Some did, a lot of them didn't. But his book helped emphasize the importance of it. All right, so on to his sequence. Name for him. So I would definitely add him to your mathematician list. He's part of that. But this sequence, instead of having a particular number to multiply or add with like we had in our previous examples, in this one you take whatever the last 2 numbers are in the sequence and you add them together to get the next number in the sequence. So like we start with 1, 1. Well, if you add 1 plus 1, you get 2. If you add 1 plus 2, you get 3. If you add 2 plus 3, you get 5. If you add 3 plus 5, you get 8. And you could keep going. Like if you do 5 plus 8, you get 13. If you do 8 plus 13, you get 21. If you do 13 plus 21, you get 34. If you do 21 plus 34, you get 55, and so on. So you could keep going with this sequence. You don't have to stop at 8, as shown by the ellipsis or the dot, dot, dot. You just take whatever the previous 2 numbers were and add them together. Typically with the Fibonacci sequence, we do start with 1 and 1, but you can have a sequence that's Fibonacci-like, where you start with different numbers and still follow that same rule. That rule is a recursive rule, where you're taking something that's already there and using it to get the next something, and then taking the new thing and one of the previous old things, applying your rule, getting another new something. Like you just keep going back, and it's almost like a spiral. I don't want to say circle because you're not coming back to the same numbers, but it's like you're spiraling along using what you previously had, applying your rule to get your next new element here. Well, in a little while, in a video or two, we're going to talk about fractals. And fractals also use recursion. But for now, we're just applying this to the Fibonacci sequence. All right, so a little bit more about the Fibonacci sequence. When Fibonacci first introduced it, he introduced it in his book that I had mentioned a minute ago, the Liber Abaci. And when he did, he gave this scenario of a pair of rabbits that's going to reproduce. You have to give the rabbits a month to mature, and then the following month after reaching maturity, they produce a new pair of rabbits, a male and a female. And each new pair will take a month to mature, and then after that will beget another pair every month. So every pair of mature rabbits every month will beget a new pair. And he showed that if you have a scenario like this, I'm not saying it's a realistic scenario, I'm just saying if you have a scenario like this, eventually, as you go along month by month and see how many pairs of rabbits you have, you will see the Fibonacci sequence. Okay, so in the interest of trying to be real clear with the colors here, in month 1, maybe I should write month 1. In month 1, you have your pair of rabbits. I'll do pink and blue. I know the colors are totally a social thing, social construct. In fact, little side note, pink wasn't always for girls and blue wasn't always for boys. Years ago, it was actually the reverse. Pink was often used for boys. But department stores decided to dictate pink for girls and blue for boys in their advertising, their catalogs. I heard that it was first Sears, Roebuck and Company, but I'm not entirely sure if it was them. But it might have been the JCPenney catalog. You know, one of those, they dictated those colors, and that's the way it's been ever since. Pretty silly if you ask me, but anyways. All right, so sorry about the tangent. You'll find that as you're around me, I go off on tangents a lot. So month 2, your rabbits aren't mature yet. In month 2, they reach maturity. So you'll still have your first pair of rabbits. They haven't reproduced yet. But then when you get to month 3, you still have that pair of rabbits, but that pair is also going to reproduce. So you're going to have the original pair still in existence. Nobody's going to die off in this example. And then they now have babies. So in month 4, you're going to have your original pair. Your babies have to spend some time maturing. But your original pair is going to have a new pair again, have another set of babies. So the rabbits continue to have babies, adding, more brothers and sisters there. And this just keeps going in this pattern. Okay, so month 5, you have your original pair. The newest babies still have to mature, but the first set of babies is matured now, and also can have a pair of babies. So let me see here. So original pair, the new babies still have to mature. The mature babies still exist. And then, let me see here. Something got thrown off. Let me look at this. Try to keep track here. Woo! All right, so original pair's there. Those babies are there. Those babies haven't matured yet. This pair's having some new ones. All right, what did I miss? I wish I was in class so you guys could tell me, hey, Miss Schofield, this is where you're wrong. All right. So original pair matured. Then once they reached maturity, they stayed around, had a new pair. Then they stayed around, had a new pair, while the first pair had to mature. Oh yeah, they have to have a new pair too. So they stay around. and I forgot to add in their new pair. That's what it was. So they had to have a new pair also. They keep having new pairs. Ooh. That's what I missed. Okay, so in month 5, the original pair still exists. They had to reproduce again, have a new pair. Their newest set of babies still just had to mature. Their first set of babies are still around, but also now starts reproducing. And it continues in this pattern over and over and over again. I think I'm going to run out of space in a minute trying to do this. And it starts to get a little harder to think about. Okay, so your original pair still exists. They have a new set of babies. And then their newest babies just have to mature still. This set of babies here still exists. Plus has a new set of babies. This one still exists, has a new set of babies. This one has to mature. So so when you go across and look at this, you have one pair originally. They still existed in month 2, but haven't matured. They're just maturing. Month 3, they still exist. Now they reproduce. Month 4, they still exist, reproduce again, plus new pair. The babies had to mature, so that was 3 of them. Month 5, original pair still exists, reproduces. Newest set of babies matures. First set of babies, original set of babies is still there, also reproduces. So that's 5. Then month 6, original set still there, reproduces. That set of babies from last month just matures. One of the older sets of babies is still there and reproduces. Another set of older babies is still there, reproduces. And their babies are now mature and reproduce. Now are maturing. They're getting ready to reproduce, but not yet. So it's like you got the grandbabies in there too now. And that's 8. And you could continue this on and on and on, and you would still see the Fibonacci sequence as these rabbits keep reproducing. So next you would have 13 pairs, and you'd have 21 pairs, and so on. So that was the example that Fibonacci used to demonstrate his sequence. Okay, and as I mentioned early on, the sequence can be seen all over the place. If you take a walk in nature, or even just buy some flowers at the grocery store or something, you can often see Fibonacci in the numbers of petals, in the numbers of leaves, in the spirals in the petals or the seeds, all kinds of places in nature. If you take a sunflower, like you can see a picture in your book, but if you take a sunflower and look at the mature seeds in the middle, they're in a spiral pattern. And those spirals, if you count them, there's a clockwise pattern and a counterclockwise pattern. Often the numbers of spirals going around are Fibonacci numbers. And then there's a lot of plants too where their leaf pattern is a spirally pattern and the numbers of leaves is Fibonacci numbers. Then I took this picture of a pink perfection camellia when I was at Bach Tower Gardens years ago. And I loved that it was a perfect example for this class. Because if you look at the pretty pink petals here, they are in a spiral pattern. And if you start counting the spirals, I've got 1, 2, 3, 4. It's so easy to start losing track. 5. Right there. 1, 2. Let me try redrawing that. Sorry. Nope. Okay. I've got 1, 2, 3, 4. Yeah. And then you got one more right there, 5. So you got 5 there with that whole Fibonacci number. And then I was looking at some of the other camellias, and they also had Fibonacci numbers for their spirals. So 5 being a Fibonacci number. It's pretty cool, huh? If you take a pine cone, like in class I usually have a pine cone to show you, but if you turn it on its butt end, you'll see that the bracts are in a spiral pattern, and often the numbers of spirals there are also Fibonacci numbers. Pineapples, now not SpongeBob's pineapple, the people who drew that weren't very correct, but if you look at a pineapple in a grocery store, the bracts on the pineapple are in a nice spiral pattern also. Piano keys, I'll draw you an example of that in a minute. Family trees of bees, so all kinds of things. And if you want more examples, you can click that. You can go to that link there and see some cool stuff too. The plants, the reason it ends up being in that spiral pattern is that as the sun, seems to be moving across the sky, the plant needs to rotate in order to make sure there's ideal sun exposure on the entire plant. And that rotation, and as it's growing, helps contribute to some of that spiral pattern. And then at the same time, the pinecone bracts and things, they don't go strictly side by side. Like if your pinecone bracts are kind of this shape, you'll find they're a little bit staggered when they lay on each other, because that helps them to use their space as efficiently as possible, while also allowing every bract to have that equal exposure to what it needs, to the sun, to the water, whatever else it needs. All right, so I mentioned piano keys. For those of you who are musicians or have ever tickled the ivories, you're familiar with the concept of octaves. You think about octave, 8, like an octet or an octagon, 8. For the sake of simplicity, let's say we start with middle C on your piano. A complete octave. Notice that there's 8 white keys. And you'll also notice that for your black keys, which gives you your sharps and your flats, they go in kind of an interesting pattern. There's not a black key every single time, but you have 2 black keys there, and then you have another set of 3 black keys here. So you have 2 there, 3 there, so 2 plus 3 gives you 5 black keys. So those are all Fibonacci numbers. So you see it right there on your piano, 2, 3, 5, 8, and so on. I mentioned family trees of bees. Well, for bees, a male bee comes from an unfertilized egg from the queen, the female. So a male bee only has one parent, the female, the queen. Her unfertilized eggs become males. And then the female bees have to have 2 parents. They have to have that fertilized egg. So the female bee will have both a male and female parents. And you can keep tracing this back. Each male bee would only come from an unfertilized female bee egg, while each female bee would come from a fertilized egg of male and female. Female bee needs both male and female. Male bee just needs female. And so forth. So if you kept going back, you would see that as you go further back into a male bee's lineage, the numbers of ancestors in each generation there ends up being Fibonacci numbers. So that's another way you could see that. If I went one more step, I'd have 8. If I went another step, I'd have 13, and so on. And if you play with the the Fibonacci sequence, you can also get something called the golden ratio. You start taking successive ratios of the Fibonacci sequence, you will approach something called the golden ratio, which is that number there. So if you do the square root of 5 in your calculator, add 1, divide by 2, you'll get a decimal that starts out like that. It's an irrational decimal, much like pi. it goes on and on forever, never starts repeating over, never stops, you know, it's infinite. So like right now, if I do 5 square root, the square root of 5 is already irrational, so that's what contributes to this being irrational. And then if I add 1 and divide by 2 right now on my little scientific calculator, I actually get 1.618033989. And this just, you know, keeps going. The calculator has to stop because it has a certain size screen, but that will actually keep going on and on if you kept working on it. You might also hear this number be referred to as phi or phi, symbolized with that Greek letter. And you start hearing about the golden proportion or divine proportion. You also might start hearing about the golden rectangle. All of these things are also found in nature and out and about, and found in human preferences and art. Let me just kind of show you real quick, though, what's happening with the Fibonacci sequence and how this is coming about. Fibonacci sequence, we got 1, 1, 2, 3, 5, 8, 13, 21, 34. That's as far as I'll go. If you do 1 over 1, you get 1. If you do 2 over 1, you get 2. If you do 3 over 2, you get 1.5. If you do 5 over 3, you get 1.6 repeating. If you do 8 over 5, you get 1.6. If you do 13 over 8, let's see, start putting this in my calculator just so I don't make mistakes and stuff. Normally I'd make you guys do this for me, but you're not here. Well, you are and you aren't. You're not here in real time. All right, 1.625. And then if you do 21 over 13, you get 1 point, it's like, it starts being some crazy decimals, 1.615384615. If you do 34 over 21, you get 1.619047619. You know, and you could keep going. You have to stop somewhere though, because this could go on forever. But you might notice that I alternated top and bottom. The top numbers, notice that they get bigger. They go from 1 to 1.5 to 1.6 to 1.615. And notice the bottom numbers start with 2 and get smaller, like 2, 1.6 repeating, 1.625, 1.619047, etc. So notice that, you know, as you go along, the ratios are going in different directions. One's starting smaller and getting bigger, the other one's starting bigger and getting smaller, but they're both approaching that golden number, that divine proportion or divine ratio. They're both approaching that square root of 5 plus 1 all over 2, or 1.618, etc. So it's a limit, you know, as we do this ratio to infinity, phi is the limit. So as mentioned, you know, there's different things that you can see the golden ratio in. Human anatomy, or at least our perceptions of the ideal form. Human anatomy isn't perfect to this, but our perceptions of the ideal human form involve the golden ratio. The Egyptian pyramids, example of ancient architecture. Parthenon also. More recent architecture too. If you start looking at some buildings, you'll find that the golden ratio and then the golden rectangle are involved. The chambered nautilus shell involves the golden spiral. And again, just human preferences, like in advertising or packaging, they'll often use the golden rectangle, golden ratio, because they know that that's what people's eyes are going to be attracted to. If you want a whole lot of more of cool examples, check out that link there. But, you know, I mentioned a few there, like when I mentioned the human anatomy. Keeping in mind, I am not an artist. Let's say you have a person You art majors better not be laughing at me. Ooh, wow, that person's head's really bad, isn't it? I don't want to erase the whole thing. Dang it. All right, maybe I should do this. It's looking more like a sea lion or something. Whew. All right, whatever. There's a person. If you start looking at the ideal form, they would say, well, like if you take the head measurement as a unit, then from that head down to the midsection would be 1.618 units. So remember, we're talking ratio here, not exactly like 1 foot and 1.618 feet, but like ratios, like whatever measurement your head is, times that by 1.618, and that should be the measurement from the neck to the waist. Or if you take the top of the head to the waist as 1, then from the waist down to the floor should be 1.618. And obviously I'm not drawing to scale. People's legs usually aren't that short compared to their torso, but it's just, you get the idea. Or if you want to look just at the midsection, you can look at like from the knees to the bottoms of the feet as 1. So then the midsection to the knees would be 1.618. So that's just kind of an example with the human form. And I mentioned the golden rectangle. You can have a rectangle where, not all rectangles are golden, but in the golden rectangle specifically, if it has the right proportions, you would be able to draw a square here that both have the same, the same side lengths, and then have this rectangle here where your length over your width, that ratio, or A plus B over A, would be the same ratio as A over B. And that would be square root of 5 plus 1 all over 2. So this is called the golden rectangle. And that one, like if you like Kit Kats, like I do, Kit Kat, it's the original size is a rectangle, and it fits the golden rectangle. This is where you might start seeing like credit cards and other things fitting the golden rectangle. Another really cool thing about the golden rectangle is you can draw a spiral in it, and that's where I mentioned the chambered nautilus shell earlier. In a golden rectangle, you have the square here, but you can take the remaining rectangle and partition that into, and it is another golden rectangle that can be partitioned into a square and another golden rectangle. Each time you partition this, you can make a square and a smaller golden rectangle. And you could keep going to infinity in a spiral pattern, like this. It just keeps going and going, smaller and smaller. So with a rectangle that has those particular proportions, phi, will be able to be subdivided into more golden rectangles that get smaller and smaller, making a square and another golden rectangle. And then if you wanted to draw a spiral, starting with this far corner here, drawing an arc to that corner, you could then do the same thing in each square. You could keep going around and drawing an arc. And this just keeps going. And that makes that golden spiral. An example of that was the chambered nautilus shell. Oops. All kinds of examples. I encourage you definitely to read your book and then try out some of the homework. The homework has a bunch of other hidden treasures, including Pascal's triangle. Pascal's triangle has a lot of cool hidden things, but specifically you can start seeing Fibonacci in it. Pascal's triangle starts with a 1 on top, then a 1, 1. And then you just keep bringing ones down, but you add 2 numbers and put that result, beneath them. So like you'd have 1, 1 plus 2 is 3, 2 plus 1 is 3, 1, 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1. So you've got a little bit of that recursion type sequence going on, but you start playing with this and you start seeing Fibonacci numbers in different diagonals and in other places. Like you might look at this diagonal here and notice that that adds up to a Fibonacci number. You start playing with Pascal's triangle and you can see Fibonacci in it. Pascal's triangle is also useful in other areas, like in algebra. When you're trying to multiply binomials, it can help you with coming up with your coefficients. Just all kinds of things. Google Pascal's triangle. Try to find videos and stuff on it. I'm warning you, it's a rabbit hole, but it's a fun one. So, all right. So let me leave you with that. And when we meet up again, we'll be continuing some more geometry fun. I believe the next video in this sequence has to do with tessellations. And then later we'll be doing one with fractals and just all kinds of fun topics. So I look forward to joining you again. And for now, just go explore.